Okay, so we have Kuldeep Purohit from NSU Baroda, and he's going to talk about rotating scalar field and formation of Bose stars.
Yeah. Am I audible? Yeah. So first of all, I would like to thank the organizers for giving me the opportunity to give a talk on the project which we are recently doing. So the topic of my project is rotating scalar fields and the formation of Bose stars. So my talk is organized as follow. So first of all, I will motivate that why the study is important, then introduction and methodology, and then I will summarize the results. So the motivation lies here that recently the work has been done by Levkov et al. And Chen et al. And they have studied that how the formation of Bose star-like structures or mini clusters is being done. And they have done the work in kinetic regime. They have also studied it with self-interaction with repulsive and attractive self-interaction. But one thing was missing in that, which was the angular momentum in the initial scalar field. So what will happen if we are having an angular momentum in the initial scalar field? What will happen? So our aim is that whether with introduction of angular momentum in the field, the star will get formed or not. And even if the stars are formed, what will be the change in the properties of the star? So the basic equations which we are working are the this Gross-Pitaski-Poisson equation. Since there is addition of this angular this self-interaction term, so this equation, if you see equation number 1, the first term corresponds to the Heisenberg pressure. The second term is for the gravitational potential, and the third term is for the self-interaction term. It is coupled with the gravitational potential. So these are the system of Gross-Pitaski-Poisson equation. Equation number 1 and 2 are written in dimensionless form, and they can be rescaled with the given scaling terms. So this is the basic equation which we are going to use. And now the main thing is that how to design the initial conditions. We are not talking about the Bose star which is already formed. We are understanding the scenario where there is an initial classical scalar field and how it will get transformed into a Bose star. So we are taking initial conditions. So initial conditions have been designed in this way. So we consider a function phi, which is a combination of two functions, phi1, which is a basic Gaussian, and phi2 is the angular momentum term. So this function is responsible to add angular momentum in the system. The small l is the term which is the scale, the control parameter, and the angular momentum in the system depends on the value of small l. So now this is not only limited to this. We are taking random distribution of the particles in the scalar field. So we are now multiplying this function. We are taking this phi in the momentum space, and then we multiply it with a random phase. So now this is randomly distributed initial condition. And now we back Fourier transform these conditions, and we get the initial conditions in the coordinate space. One thing I want to mention here, that if I make phi2, which is the angular momentum term, equal to 1, then this will reduce to that earlier works by Levkov et al. So this is the thing. Here I also want to mention one more thing, that there is nothing special about this function which we have taken. You can take any function of your choice to introduce angular momentum in the system. As long as the magnitude of this angular momentum is same, it will not affect the condition. So we have tried various prescriptions of angular momentum in the system, and the results were not changing. So these results are quite general in nature with angular momentum in the system. Yeah. So I just want to visually show you that how the initial conditions look like. So the top figure which you are seeing here, there is a random distribution of particles with no angular momentum. So which is similar to Levkov et al. The below figure is our initial conditions, where you can see that in first two figures there is an initial stretch. That stretch has been due to this angular momentum introduction in the system. So we have added angular momentum in the xy plane. So you can see that in the xy plane there is a stretch, and so that stretch is the effect of that phi2 initial condition which we have taken. So this is the visual representation of our initial conditions. And here I want to just pictorially show you that how this field which we have taken. So this is the first figure, which is your initial condition, and at certain times how it evolves, and ultimately a Bose star is formed. So this is how the Bose star evolution takes place. So this is how, so this is a rotating scalar field and how it evolves into a Bose star. So the final picture which you are seeing is the Bose star. So now we have also done, before going to the numerical results which we have got taken, we have also done some analytical things also. So I just want to show you that if a stationary star is formed now, so we can take this approximation that d psi by dt can be equal to omega psi. So omega psi is the energy of the bound state, And we can also replace the spatial derivatives with 1 by L. So this is how the Gross-Pitaski-Poisson equation look like in equation number 3. Now, here, if you see the thing, so things are same. The first, this term is due to the quantum pressure. The middle term is due to this gravitational pressure, and the third term is due to the self-interaction term. Now, for a Bose star to form or a gravitationally bound object to form, one thing is necessary, which is that the gravity should dominate over the self-interaction. So if we compare the second and third term and neglect this small and tilde term, then we are getting a condition that G by L over G by LB square should always be less than 1. So here, this is the G is the self-interaction parameter and LB is the size of the Bose star. So G by LB square should always be less than 1. We have done our simulations and we have seen that this condition is always satisfied up till G by LB square is equal to 0.9. Once we go beyond 1, the Bose stars are not formed. So this analytical result is quite consistent with our numerical results also. Another is that we can also estimate the size of the formed stars. So just solving this equation number 3 again, we get an estimate of the size of the bound states. So this is the equation. Here, one thing is to be noticed that if we take attractive self-interaction, which means that G is equal to negative, and compare it with G is equal to 0 case, the size of the Bose star will be more compact for attractive self-interaction. If we take repulsive self-interaction, then the size of the Bose star will be bigger than the compact size. So this is what we have seen from our analytical calculations, and this is also consistent with our numerical results. So now let's move on to the methodology which we are using. So we have used to evolve the Gross-Pitaski-Poisson equation. We are using a publicly available, we are modifying the publicly available axionics code, and we are evolving the time-dependent Gross-Pitaski equation using the 6th order pseudo-spectral method to see that how the angular momentum changes with time or how the angular momentum evolves with time. We have plotted the vorticity magnitude at various times and see that how this angular momentum is evolving with time. And also we have seen that when there is no self-interaction and no angular momentum in this box, this should reduce the earlier results which were done by Levkov et al. So yes, it is also consistent with Levkov et al. Results. And to see that when is actually the star formation process beginning, we have 2 checks. So first is that how to check the evolution of maximum amplitude of the system. So we track that at all the times what is the maximum density of the system, and after a certain times the density of the star of the box start increasing. At that point we say that yes, the star formation has begun. And the second test is to plot the Fourier correlator function, which is also the power spectrum. So I will show you both this test that how this looks like. So let me show you the results. Due to the constraints of time, I am only showing you the results with repulsive self-interaction, but the qualitative features remain same for other things also. So this is the first part where we have seen that how the evolution of maximum density changes. So initially till you can see that for the top figure there is no angular momentum in the system, only repulsive self-interaction is there. So the condensation time begins around 12,000 and the start process begins. In the second, we have taken angular momentum equal to 3, and you can see that the star formation process has delayed. When angular momentum is equal to 5 in the box, the star formation delay has been increased. So with introduction of angular momentum, okay, the star formation process will delay. The another is plotting the Fourier correlator. So the bell-shaped curve, which you are seeing on the right-hand side, is the particles in the normal thermal distribution, and this peak at negative omega is an indication that a bound state has been formed. So this negative omega is a signature that a bound state has been formed. So you can see that there is a negative peak for all the angular momentum cases. So we can say that a gravitationally bound state has been formed. So these are the 2 tests which we do for the star formation process. Again, I want to show you the same thing, which is the evolution of maximum density. But I want to also here mention a few points that you can see that condensation time has been delayed with increase in angular momentum, but also not only the condensation time, but how this density changes with time has also been changed. So the slope also changes. So it will also affect the mass, what is the compactness, everything will be affected with introduction of angular momentum in the cloud. So here now I want to show you that our initial field is having an angular momentum. But that necessarily doesn't mean that all the angular momentum is transferred to the star. So we have to check that what happens. So what we are doing is we are plotting the vorticity magnitude. So these black contours which you are seeing are the vorticity, are the contours of vorticity magnitude, and this density which you are seeing is basically the star formation region. So this is the case for attractive self-interaction, and you can see that all the vorticity is lying outside the star formation region, which means that the star is not having any angular momentum. So for attractive self-interaction, you cannot have a rotating star. All the angular momentum will be shaded outside, and the star which will be formed will be stationary in nature. Now we are getting slightly different case or completely different case when we are having a repulsive self-interaction. Here we are showing you how the vorticity evolves with time. And initially there was some vorticity in the system, but after certain times you can see that the contours are diminishing. And after a certain time, when the star is totally formed, you cannot see the vorticity contours outside. So it means that the vorticity has gone inside the star, and the repulsive self-interaction has a rotating star like case. So it is also consistent with the earlier stability analysis by Levkov et al. And they have shown that if you want to have a stable rotating star, you must have repulsive self-interaction thing. So our results are also consistent with the instability analysis of other guys. Yeah, now I want to summarize my results. So I want to digress on three important results which we have seen in our results. That we have put an upper bound on the self-interaction coefficient, and it is also consistent with our numerical results. The second point is that the introduction of angular momentum not only changes the condensation time of the system, but also it affects the compactness, it affects the mass and other features of the Bose star. The third thing is that for the formation of rotating Bose star, one must have repulsive self-interaction in the system.
Yeah, so questions? Yes.
Yeah. So I was just trying to understand the results that you got numerically. Theoretically, how would we understand? So correct me if I'm wrong. So basically, if you do not have repulsive self-interaction, so in principle, if you want to solve these spherical solutions out of your Klein-Gordon equation, so you will expand it into a spherical harmonics, right? And the ground state, which is L is equal to 0 mode, would be possible. But the moment you start repulsive self-interaction, maybe L is equal to 0, which is the lowest energy configuration. Maybe it is not energetically feasible, and because of which your higher angular momentum solutions are possible. Is that the understanding?
Yeah, this is how the instability analysis is done, but it is done in more detail. So stability analysis has been already done. When you take initial spherical structure and when you start to rotate it, what will happen that it will form a Saturn-like ring outside. So all the angular momentum will be transferred into that Saturn-like ring, and the star will be stationary in nature. So even if you take, here we have taken an initial scalar field at time t equal to 0, and we are seeing the formation scenario. But what you are talking about is the stability scenario, where at time t equal to 0, you are already having a star, and you are trying to see that if I introduce angular momentum in the system, what will happen. But at that time, what will happen that even at that point of time, if you are having a attractive self-interaction or no self-interaction, the angular momentum will be shaded out, and the star will be non-rotating at that point of time itself. Mm-hmm. No, we are just taking, it is a random initial fluctuation, random initial condition, random distribution of axion-like particles, nothing motivation. And you can also change. I have already said you that there is nothing special about this phi2 initial condition, which is there to introduce the angular momentum in the system. You can take any function of your choice. As long as the overall magnitude of angular momentum is same, the overall results will be the same.
Is more questions? Okay, if not, thanks the speaker. So, thank Thank you for nice talk.